Hi, I'm Dr. Tim Komar, and today we are going to be talking about the derivation of the derivatives of the inverse trigonometric functions. First one we're going to look at today is the derivative of the arcsine function. Its derivative is going to be 1 over the square root of 1 minus x squared. Here's how we're going to go about proving this now. So if we have y set equal to arcsine of x, we can rewrite this equation in the equivalent form, sine of y equals x. Now we can implicitly differentiate this equation with respect to x. And on the left-hand side, we're going to get cosine y times dy dx by the chain rule and just a good old 1 on the right-hand side. Now, since y is arcsine of x and x is between -1 and 1, the y values here, the outputs of the arcsine function, lie in the interval from -pi/2 to pi/2. That tells us that our cosine values of those y's now are going to lie in the interval from 0 to 1. Now we can solve for dy dx over here, and it's just going to be 1 over cosine y. Just wanted to be careful we weren't dividing by 0. So here we go. But now we want to get this back in terms of x. We can use our favorite Pythagorean identity, sine squared of y plus cosine squared of y is 1. And we can solve for cosine of y and take the square root. And again, we just said that the values of cosine are between 0 and 1. So all we really need here is the positive square root. And better yet, since x is sine of y, we can write cosine of y in terms of x as just the square root of 1 minus x squared. We then end up with our derivative formula, where our derivative of the arcsine function is 1 over the square root of 1 minus x squared. Now on to the arctangent function. The domain of arctangent is any real number, and its derivative formula is going to be 1 over 1 plus x squared. And we are going to prove this in the same manner. So here we have the equation y equals arctangent of x. We're going to rewrite it in the form tangent of y equals x. And just like before, we're going to implicitly differentiate with respect to x. On the left-hand side here, by the chain rule, we're going to get secant squared of y times dy dx equals 1. And yes, secant squared is going to be positive wherever it's defined. And just to take a quick review here of what's happening with the trigonometry, if y is arctangent of x, yeah, the y values here are going to lie in the interval from -pi/2 to pi/2, which tells us that our cosines of y's are going to lie in the interval from 0 to 1. So the secant squared values are going to lie in the interval from 1 to infinity. So if we solve for dy dx, we're going to get 1 over secant squared y. And now we want to get it back in terms of just x. We are now going to use another one of our Pythagorean identities, 1 plus tangent squared of y equals secant squared of y. And using the fact that x is tangent of y over here, yes, secant squared of y is just 1 plus x squared. And then we get our beautiful derivative formula for the arctangent, 1 over 1 plus x squared. We're now going to take a look at the derivative of the arcsecant function. We're only going to worry about the cases where the absolute value of x is greater than 1 here. We're not defining this at the points where the absolute value of x is 1. So here, our derivative formula is going to be a slightly more complicated looking formula, 1 divided by the absolute value of x times the square root of x squared minus 1. We prove this in just the same way. We said y equal to arcsecant of x, and rewrite it as secant of y equals x. Implicitly differentiate again. Remember, the derivative of secant is secant y times tangent y times dy dx. There's a little chain rule here, equals 1. Okay, so I want to keep track of the plus or minus signs here a little more carefully here to end up getting our final formula over here. So if our inputs into the arcsecant function are greater than 1, that's going to correspond to y values, the output values in between 0 and pi over 2. And that tells us that our tangents there are going to be positive. Similarly, if x's are less than -1, that's going to tell us that our y values are going to be between pi over 2 and pi. And in that case here, our tangents of those y's are going to be negative. So we're going to keep that in mind, and we're going to be using that as we move on over here. So the good news is secant is never 0, and our tangent is never 0, so we can divide here to get that our derivative is going to be 1 over secant y times tangent y. And as in our last two derivations, we simply want to get this into a formula just in terms of x. We're going to use that same identity we used before, the 1 plus tangent squared y equals secant squared y, and this time x is secant of y. That tells us that tangent squared is going to be x squared minus 1. So if we solve for tangent of y here, yeah, we're going to get plus or minus the square root of x squared minus 1. The question is, when is this positive? When is this negative? So here, looking back at our analysis that we did a couple minutes ago of when the expressions came out positive or negative, in this case here, the tangent of y is going to turn out to be the positive square root when the x's are greater than 1. And it's going to turn out to be the negative square root when the x's are less than -1. And here's just a little bit of fancy algebraic manipulation over here. If we're looking in the case that x is less than -1, so x is a negative number here, we are going to be able to write secant y times tangent y as x times negative of that square root of x squared minus 1. Okay, move the negative sign over here. But notice here, since x is a negative number, negative x is just going to be the absolute value of x over here. And again, the same formula is going to hold if x is greater than 1 and positive over here because x will be its absolute value, and the tangent will be the positive square root in that particular case. So rewriting our derivative in terms of x now, we have that our derivative is 1 over the absolute value of x times the square root of x squared minus 1. So what about the derivatives of the other three inverse trigonometric functions, our cosine, our cosecant, and our cotangent? Well, from these identities over here, we can express our cosine in terms of pi minus arcsine of x. In other words, we can, when we take the derivatives of that, we're going to see pretty readily that the derivative of our cosine of x is just going to be minus the derivative of arc sine here. And same with the other two pairs. So we've really done all the hard work. And what we are going to be left with here is our 6 derivative formulas for the 6 inverse trig functions. Again, I'm Tim Komar. I'm available for mathematics tutoring. Like this video, watch other videos. Next video is going to be one showing examples using these derivative formulas, and look forward to seeing you soon. Thank you.